So we have a 12 Newton force with fixed orientation doing work on a particle, so it's just from one direction, moves through a three-dimensional displacement. So the particle moves through this vector. So it's got three components, an x, a y, and a z component. This is the x, this is the y, this is the z. We should be getting pretty familiar with breaking up our vectors into those different components now. It's asking what the angle between the force and the displacement is if the change in the particle's kinetic energy is this value. So we're going to use the work KE. We're just calling it K at the moment, aren't we? Kinetic energy theorem. That basically just says that delta K, the change in the kinetic energy, is equal to the work done. We also know that the work done is equal to F dot D. We've been doing that one to death, which is equal to the magnitude of F, the magnitude of the displacement times cos of the angle between them. And that's what we're looking for, that guy. So we also know, this is some other data we have, that the magnitude of F is 12.0 newtons. We're given that in the problem. We can also calculate the magnitude of D just by looking at this vector and looking at its scalar components. dx squared plus dy squared plus dz squared. And if we take those components, 2, minus 4, minus 3, and square them all together, I'll better draw it here, we're going to get 2 squared plus minus 4 squared plus 3 squared equals 5.39 meters. So we've got those guys. We're going to be able to then use this information to work out if the particle, change in the particle's kinetic energy is 30 joules, we should be able to now work out what the angle is. So if we know that delta K is equal to, now we know it's equal to F D cos theta, just from the big arrow up here we worked out before. So therefore, cos theta equals delta K over F times D. Those are magnitudes. So theta equals cos minus 1 delta K over F times D. So theta equals cos minus 1 30 over 12 times 5.39. So we've already worked out 62.3 degrees. That's the answer to the first one, and then very easy to find out B just using the same expression. So cos minus 1 delta K over FD is cos minus 1 minus 30 over 12 by 5.39, and we get a different angle, 118 degrees. Reasonably easy, but we had to put together a few things there, the work kinetic energy theorem and the work done is F dot D. This is a conservation of energy problem. So we have a potential energy versus position graph here for a 2 kilogram particle. Let's we can look at this potential. It makes it easier if we just think it's a gravitational potential energy. Well, it makes us quite intuitive to think about it if we think that way. It's got some values of this point here is 9 joules. This point here is 20 joules. And this point here is 24 joules. And this one is, so UB is 12 joules. That's for the potential energy. So the potential energy of those points is that value. A couple of things that we can point out are that in this region here, the change in the potential energy, which equals the change in kinetic energy, is equal to 0. So we're not going to have any change in that region. So the kinetic energy, potential energy, anywhere in that region is 0. And for most of this region, that's the case as well. So the change in mu equals change in K equals 0. So there's nothing happening there. So I just want to outline a couple of regions at sort of points. So at this point B, and then at some point A here, and then some point C here. Okay, so we're looking at a few different regions. We're asked to find the speed of the particle at x equals 3.5, so that's in region A, and at 6.5, so that's in region C. So it's A is there and C. So we're asked to find the speed of the particle at those points. We're going to have to use conservation of energy, so look at the kinetic energy to find the speed. Something that I'll point out here is that at height B, so at 12 joules so of potential energy, so at this point, there's kinetic energy of 4 joules. And this is a conservative force. We've been told there's only conservative forces acting on this guy. So then we know immediately that the energy, the total mechanical energy, is going to be 12 joules plus 4 joules, 16 joules. So the total energy of this particle is 16 joules. So we can then set a limit at 16 joules on this graph as the total energy of the system. Okay. Which means that some particle sitting inside there, it can only ever obtain 16 joules of energy. That could be kinetic energy or potential energy. So it's basically going to run up and down the sides of this thing. You can think of it as a potential well. So it's trapped in here. The particle is going to be sort of moving around. It's going to go over this one, up here, and it's going to stop here, and it's going to go back again. So you can think of it like a funky skateboard ramp. The particle can't escape because at this point and this point here, the K is 0. So here and here is also 0. And that's what I'm talking about in this question by what is the position of the turning point on the right. So this would be the one on the right. And this would be the one on the left. Okay, it's a turning point. So it's where the kinetic energy goes to 0 and the particle turns around and rolls back down the potential well. So that's some explanation. So let's go on to start solving the problem. First of all, let's look at question A. So question A is saying, what is the speed of the particle in region A? So we know that the potential energy, I'll just make that work properly. The potential energy in region A is 12 joules. 9 joules. Go back. It's 9 joules. And the total energy is 16 joules. Then the kinetic energy has to be 16 minus 9, which is 7 joules. Okay, the total energy has to add up to 16. So we've got 9 of potential, we must have 7 of kinetic energy. Okay, so then it's pretty trivial. Then we can say kinetic energy equals half mv squared. So V equals square root of 2k over m. Just square root of 2 times 7 divided by 0. This is all divided by 0.200. And that comes out to be 8.37 meters per second. So in region A, that's our velocity. And it's not going to change because there's no change in the kinetic energy in that region. If we do that again for region B, so that's for question B, it's asking for x equals at 6.5 meters. So sorry, region C, in region C, so in this region here, we can calculate that as well. But in that region, oh, UC, dodgy pen, UC equals 0. So the potential energy at the bottom of that well at region in this area is 0. So therefore, all of the kinetic energy, all the energy must be in the kinetic energy, so 16 joules. We can use the same expression, root 2 K on M. To find that, we just go root 2 times 16, divide by 0.200, and that comes out to be 12.6 meters per second. So at the bottom of that well, we've got a much higher velocity. You can imagine if you're rolling from the left there, rolling into the bottom of that hill, then you roll down a steeper hill, then you're going to have a higher velocity at C than B, than A. So have a think about this in terms of this being a gravitational potential well. That makes it a little bit easier to understand. So C and D are asking about the turning points on the left and the right. We've already sort of talked about this. We know that when we've got our total energies like this at 16 joules, then these are the points here and here where we're going to turn around. So our kinetic energy is going to be 0 at those points. So yeah, K equals 0 here and here. So we need to find out what those points are. So we know a few things about this. Well, what we're going to do is find, well, what we should do is find the equation of this line here. That's going to help us because we're going to be able to find out what the, really what we want to find is this point here on the right and this point here on the left. So we can see roughly by looking at that this is approximately 1.7 meters, and the other turning point on the right hand side is approximately 7.7 meters, around about. So that's rough. If you could graph this, you could show that. But we kind of want to do this. We're going to need to find the equation of this line as well. So if we find those equations, we should be able to find exactly what it is. But so we know a few things about. Let's first of all, we want to find this position, which is, we'll call it XR. Okay, so it's the turning point on the right hand side. You just repeat this for the left hand side. So I'm only going to do it for this side. We know a few things about this line. We've got a point here, which we know is it's 8 and 24. Okay, it's 8 meters on the x-axis, and it's 24 on the y-axis. We've got another point down the bottom here, which is going to be 7 and 0 by the same arguments. So we've got some points there. We can find out what the gradient of this line is. So we've got x1 equals 7, and we've got x2 is 8. We've got y1 is 0, y2 is 24. So we can easily find out what the slope of that is. Remember, the slope is y2 minus y1. So rise over the run, x2 minus x1. So that comes to 24 over 1 is 24. So our gradient of this line is 24. This helps us because we're trying to fit some stuff into an equation that says y equals mx plus c, the equation of a straight line. We now have that. We don't have this yet, so we have to do some trickery to find that. So we can rearrange that equation to get c, well, moving around a bit, to get c equals, we can just choose any case or any of our coordinates there, and we can choose this one here to make it easy. So we can say c equals y1 minus mx1. Okay, we've just chosen two of our points and rearranged our equation of a straight line to solve for c. So that's going to be 0 minus 24, which we calculated, times 7, which is minus 168. That's our y-intercept. So now we have an equation for the line. We can write this. We can say y on the right, y position is equal to the gradient, 24, times xr minus 168. Okay, so we can rearrange this for XR, and we get XR equals YR plus 168 all divided by 24. Now YR in that position for XR is 16. We know that at this point the Y coordinate is 16. So that's going to be 16 plus 168 divided by 24. And that comes out to be 7.67 meters. That's very similar to what we kind of guessed. So just do that again, the same process. Do that on the left to find the gradient of this line here, same process, and you should get XL is 1.67 meters. So that works. Right, so we have a block here. This is very similar to the challenge question. I didn't give you this before the challenge question because I wanted you to have a think about it, but you have a 3.5 kilo block accelerated from rest by compressed springs. We push the spring in, let it go, and this thing accelerates and gets some kinetic energy. So all of the potential energy stored inside there because there's no friction and the spring is a conservative force, spring force is conservative, all that potential energy inside the spring gets converted into kinetic energy. So we'll just say US goes to kinetic energy. So this guy gets some kinetic energy. It leaves the spring and then travels over a horizontal floor, this section here, which has some friction. Friction meaning we lose kinetic energy. So we lose all of this kinetic energy here, gets dissipated across this surface here. It gets dissipated by the work due to friction. So let's write down some data. We have the spring constant, which is important. That's 640 newtons per meter. We have the mass, which is 3.5 kgs. We have mu k, which is 0.25. And we have delta x, so the distance over which we lose our energy is 7.8 meters. So we can draw a force diagram. You got the normal force this way, you got mg acting downwards, and you're going to have the frictional force here pushing backwards. I'll just change that to the right subscript. Okay. Pushing backwards to do some work and remove our kinetic energy. So this sort of looks like a tricky problem, but it's not too bad. So that's everything that we have. Let's go through it. So the work done due to friction is going to be what's dissipating all of our kinetic energy here. So we can just say then that the work due to friction is the force of friction times delta x. It's still in one dimension, so we don't need to worry about the vectors. Mu k, remember it's just mu kn. We know that's the equation for our normal force now. Delta x. Put in some values. 0.25 times 3.5 times 9.8. Remember, normal force is mg. And delta x is 7.8. And that gives us a value of 66.9 joules. So friction dissipates 66.9 joules of energy. That makes the next question very easy because the kinetic energy, or the change in kinetic energy, is equal to the work done. So that work done from friction is removing all of our kinetic energy. So it must be 66.9 joules. We lose 66.9 joules. And that would be the maximum kinetic energy, because maximum kinetic energy is going to be at this point here when we first hit the surface, because the kinetic energy is not going to change across here because there's no dissipating forces. It's going to be maximum right here at the friction. So that's our answer. That's very easy. Right, so for question C, we are asked about the original compression distance of the spring. Well, I mentioned earlier that over just here, that the compression of the the amount of potential energy stored in the spring is going to be converted to the kinetic energy, so we can relate the final kinetic energy back to the potential energy in the spring. So spring potential energy μs is converted to kinetic energy. So we can then say that the change in the spring energy is equal to the change in kinetic energy. So therefore, well, we have an expression for the spring potential energy. Don't confuse the little k in this equation for the k in the kinetic energy. So if we extend from an equilibrium point x equals 0 to some other position x, then the potential energy that we store in the spring is half little k x squared. Okay, so that's the potential energy stored in the spring if we move it away from an equilibrium position x equals 0. And we know that that's then equal to big K, which is the kinetic energy. So therefore, x squared equals, we can just rearrange that to 2 big K over little k. Okay, so if we want to get rid of our squared term, we have to do the square root on both sides. So therefore, x equals root 2 big K over little k, which is 2 times 66.9 over 640, which we have up here in the problem, which equals 0.46 meters. Okay, so that's using conservation of energy, using the work done by friction, using the potential energy of in a spring being converted to the kinetic energy. So a lot of different energy systems going on there.